Welcome back. I'm going to talk about how we can use gradient descent in control. And when we deal with control systems, it is more convenient to work in a continuous time setting. So, however, in the previous videos with regard to gradient descent and gradient descent with momentum, we worked on these discrete time forms. So let's see how we can transform these forms to continuous time. Let's start with gradient descent equation here. Basically, we can rewrite this equation like this. Basically, I sent this to the right-hand side and then divided each side by delta. Think about delta as the very small value, such that this represents the derivative in continuous time. So we can write this continuous time gradient descent form. W dot equals to alpha. This alpha and this alpha are slightly different, okay? So actually the alpha here is alpha divided by delta, but since this is a free variable, I am just going to call as alpha here. So this is the continuous time form. You can also use this continuous time form in the previous with the previous gradient descent material. All right, so similarly, if you have gradient descent with momentum, by doing this trick, you can have this continuous time form here. Again, these alpha and gamma does not directly correspond to what you see here, but that's okay. At the end of the day, these are all tuning parameters. These are tuning parameters. You can just choose them as you want with regard to the given application. Okay, so to make the long story short, in what follows, I am going to focus just gradient descent in a continuous time setting, where you can use the equivalent principles for gradient descent with momentum in a continuous or discrete time setting. Okay, let's start. Let's start with simple examples. Let's say you are dealing with x dot equals to u, a scalar system, and let's make x follow a given command. For this, I am considering a cost function looking like this, 1 over 2 x minus c to the power of 2. So it is, if you plot it, it is looking like, right, a function like this. So we are trying to find the minimum, and basically minimum occurs when x equals to c. So taking the gradient, basically we have delta v, gradient of v is x minus c, and I am going to choose my control signal as the negative gradient or gradient descent minus alpha. Alpha is a positive constant multiplied by this function. So our closed loop system becomes x dot equals to minus alpha v, or x dot equals to minus alpha xc. C can be a time varying command. So as you increase alpha, as you put more power to this gradient, you are going to see that you can closely follow any given signal. We start with the scalar first order ordinary differential equation. So let's look at the second order one. And this is again control signal. This second order equation pops up also in this motion constraints and feedback linearization video. If you remember, when on that video we had non-holonomic vehicle, and when we considered hand coordinates, with each coordinate basically on x and y, we arrived to this double integrator form. Now let's also have the same objective, make x follow the command. I begin with the first cost function, which is essentially the same cost function here. Again, that cost function is looking like more precisely this, and this is x minus c. We are trying to find the minimum of that cost function. And taking the gradient of v1 is x minus c. So you can go ahead and use this in the control signal like I did here, the first gradient, v1. However, using this, in the sense that using this alpha delta v1 as the only control signal, will allow X to follow command, but there will be oscillations. To dampen those oscillations, we need to also consider additional cost, basically the velocity of the position X dot. So I am considering another cost function. It is gradient is X dot. By the way, I should mention that here gradient is defined with respect to X dot. So, but generally when I wrote like this is right dv1 over dx. So unless otherwise stated, all the gradients are with respect to x, but here with respect to x dot. So you arrive at x dot. So control signal becomes the gradient descent with first cost function and the second cost function. So your closed loop system looking like x dot dot. I have a typo here, x dot dot. This is the first term, this is the second term, and alpha and beta are basically positive constants. So I am going to demonstrate this in a Matlab example, but let's also focus on enforcing state constraints using gradient descent. Let's say we are operating X, but there are some safety regions that we should avoid. For example, you want X to stay, maximum amplitude of X to stay below X max, right? For example, you're applying a command C to the system, so accidentally you applied a wrong command and you don't want your vehicle to, let's say, hit to a wall. So a position constraint. All right, so we are going to use these two cost functions and we would like to add another one, but this one will be interesting. So I am considering V3 here as our cost function that depends on X, which has this interesting structure. So here I am going to talk about how to select this constant D and this row X. First of all, if you take gradient of V3 with respect to X, you are going to obtain this form. So we are going to use this in this additional control signal theta. We are going to choose it as gradient descent minus gamma multiplied by the gradient of V3 if we are basically close to the that constraint, and it is 0 otherwise. If your system is operating away from the maximum limits, then we don't need to apply any control signal. Okay, so as you see here, this function plays an important role. I am going to choose that function rho to be absolute value of x minus x max signum of x. I think it is better that visualize this. So let's look at this figure. So this is the figure that plots that function with this rho variable. As you see, this function is approaching a high number as you get close to the x max. And the reason we use sign of x here, because we also would like to have mirror the same behavior as you approach to this other side. So the punchline is, if you use this function along with this V3, by the way, this V3 is a popular type of function, also called as the barrier function, and it is also used within the context of obstacle avoidance with potential fields. So it is a popular V3. So we are going to use a very similar one for obstacle avoidance. Anyway, about the selection of D, if you select D larger than these, basically this becomes more smoother, or so this function gets bigger. If you choose D lower, you have a narrower function that is looking like more like this, okay? All right, so since we have signum, we need to be careful in coding this. So let's jump to a Matlab example. This is the total simulation time. This is cleaning. This is the first order Euler methods discretization sampling. Initial condition for states are 0. I am choosing alpha and beta like this. Again, you can code it yourself and do a little experiment how these play role. And this is the maximum value for state limit, position limit, which is 5. And I choose the width of this function rho to be 2.5. I am choosing a command that is a sinusoidal that changes between 10 to minus 10. So when we enforce state constraints, we should see that we should never go. We should track the sinusoidal command when we are between 5 to minus 5, but if it gets beyond, we should stop because we would like to enforce state constraints. All right, so this is how I code. Basically, this is nothing different than what I just show you here. Theta is activated when this rho is less than d. So when you have a critical distance between your position state x and the state limit, this function is activated, otherwise 0. As you see here, first I would like to focus on this. This is the rho function. This is the gradient of rho, or rho prime. This is, if you are close to d, dv is this, and dv is this is dv3 actually. In the if I should be consistent with the notation here. This dv represents this delta v3. All right, so when I said we should be careful about coding this, I added also this here. Basically at the beginning, right, sine of x1 is 0. So at that time, dv should be 0 because when you are at the origin, it is when x is 0, it is not possible to violate. Without this, this code may stuck. At the beginning, you should start from a non-zero command, but so non-zero x. Just I would like to use this all over between minus 5 to 5, so that's why you need to include this to your code. And this is the control signal alpha beta term and this dv3. I'm basically coded like this. This is equivalent to x dot equals to u. It is like in a state space form. This is for data recording purposes and this for the figures. I first illustrate the case when alpha is 4, but I select beta and gamma equals to 0. So the second v2 drops out and I am not enforcing any constraints. As I mentioned at the beginning, you kind of track the signal, but you know this represents x dot. Okay, this represents x. So you have a growing oscillations in x2 and control signal getting unbounded. So that's why we needed to add this beta v2 term, x dot to the power of 2, to dampen those oscillations. Now I am using alpha 4, beta 16, and I am not enforcing any constraints. So as you see, red is the command that we would like to track, and blue is the position x. So it follows closely, and this is the velocity is nice, and here is the control signal. Now I would like to enforce constraints. I don't want this x position to exceed this 5 and minus 5 limit. I am turning this dv3 on, and I didn't code it, but I used gamma equals to 1. So you can add a gamma to your code and use a value other than 1. As you see here, we are trying to track this red command. When you hit x around, around 5, when you are getting around 5, and when I say around, it is not exactly 5 because of, when we get approach, it just stops it there. So when command is on the normal operating region, it follows the command, then it doesn't violate minus 5 constraint. And this is how x2 or x dot looks like. This is the control signal. So in this video, I just tried to show, different applications of gradient descent in control. You can use for designing a control signal, state constraints, and there are many more applications. I don't want to limit your imagination about, just by showing 3 examples. So for example, I often use it within the context of model reference adaptive control. For example, this is one of the papers published in IEEE Transactions on Automatic Control. solving one of the problems. Since weight update laws of basically model reference adaptive control signals has this fancy integrator type of an architecture, when you increase gamma, this can induce oscillations in the weight estimates. So on that paper, I considered a cost function like this, and here W hat F is basically a low pass filtered version of the W hat that doesn't contain those oscillations. And I am adding a gradient descent term to the weight update law to minimize those oscillations, which takes the gradient here with respect to W hat. All right, so another one is for improving performance during the learning process. So since adaptive controllers, learning can take some time. So I would like to compensate for, since learning takes time, system can suffer from poor transient response. So this is the error dynamics. I am adding here another term, and I am constructing that term with respect to its gradient. Maybe I should mention sooner, right? Since I am enforcing a constraint, taking the derivative, which is added to this sigma A dot equation, I am taking gradient with respect to sigma of A. Similar to here, I am adding a term here, so I am taking the cost function's gradient with respect to W hat because I am adding this term to W hat dot. Something to remember. Anyway, so this was the cost function capturing all these effect of the uncertainties. And basically, if you add the gradient of this here, it basically minimizes the poor performance effect, so it significantly improves the performance. So these are two additional applications. If you are familiar with model reference adaptive control, you can read it from here. Again, in this video, my main motivation was to show you how we can use gradient descent in control. Take care.